Now that we understand the four fundamental spaces and how they relate to how A maps a vector x to a vector in a column space, we can come up with our first practical method for solving the linear least squares problem. So how does that go? Well, notice that we want to find the x that minimizes the 2 norm of b minus ax. That's how we formulated the linear least squares problem. What that really means is that we want to find x hat such that a times x hat, well, b minus a times x hat in 2 norm is equal to that. Right? We're interested in the solution. We're not interested all that much in the minimum here. All right, now let's have a look at what that means. Well, we know that a times x hat is in the column space of A. So let's draw this as the column space of A, where in a previous week we looked at how we can always tilt a space so that we look at it from the edge so that it looks like a line. Okay? And what's really going on here is, well, let's put the origin in there somewhere just as the reference point. And what we have is we have a vector B that is not necessarily in the column space of A. Obviously, if it is in the column space of A, then we could exactly solve this problem. Okay, then the minimum would be when this is equal to 0. All right, so what really is going on here in trying to minimize this, notice that we're looking for a vector b hat that is in the column space because it has to equal a times x hat. So that lives somewhere here, but we're saying that it minimizes this, so it minimizes this distance between b and that point. So our b hat is the point in the column space of A that is closest to b, and if you think about it, if it's closest to b, then this vector right here, which is the difference between b and b hat, has to be perpendicular, orthogonal to our space. All right? So, but we're kind of reasoning through that. What do we know? Okay? Well, we know that if this here is perpendicular to it, it must live in the left null space of A. Why? Because we saw that the left null space of A is the set of all vectors that are orthogonal to the column space of A. All right? So what does that mean? That means that A Hermitian transpose times the vector b minus b hat must be equal to the 0 vector. All right? Let's manipulate this a little bit. That means that A Hermitian transpose times b minus a times x hat is equal to 0. Okay, let's manipulate that a little bit more. It means that A Hermitian times b must be equal to A Hermitian times a times x hat. That's distributing this and then bringing this to the other side. And then we can switch the order of this, and you find that A Hermitian a times x hat must be equal to A Hermitian b. So what we find is that the vector that minimizes this must satisfy this linear equation. Okay? This particular equation is known as the normal equation. And if you create this, create this linear system and then you solve it, then you're using the method of normal equations. And bingo, we have our first way of solving the linear least squares problem. Now, especially if A has linearly independent columns, then this is relatively straightforward because you can prove that if A has linearly independent columns, then A Hermitian A has linearly independent columns. In other words, it has an inverse. So then literally it just comes down to solving a linear system that only has a unique solution, and you're done. If A has linearly dependent columns, then things get a little bit trickier.